Thank you very much. Thank you very much, Bobadin, for the invitation. I'm very happy to be back after 2 years. I will be giving more high-level perspective on new emerging methods in scientific machine learning that use differentiable programming, which is like automatic differentiation at scale, for optimization, dynamical systems, and control. So these are typically 3 separate communities, but there is a lot of exciting new research opportunities on the intersections which we want to focus on. And why we want to focus on them? Because at the National Lab, we typically are driven by some practical problems from Department of Energy application space that require us to combine dynamical systems models with constraint optimization solvers and optimal control problems. And that's typically very challenging because different communities develop different theories, different tools that are very hard to integrate. So challenge number 1 is that we have really heterogeneous dynamical systems models, whether it is like black box function approximators like deep neural network, or gray box system identification methods, or very complicated component-based models in MATLAB Simulink or on Modelica languages. Then we are solving heterogeneous problems. In real-time optimization, we are formulating objectives and constraints, and we are using interior point or active set type methods to give us solution to these recurrent problems. We are using all sorts of ODE solvers to integrate ordinary and partial differential equations. And then we have machine learning optimization that's typically using stochastic gradient descent on over-parameterized models. So different approaches that led to emergence of different tools. So whether you are coming from controls and operational research community, you are familiar with tools like JUMP or CVXPy or Casadi for dynamical system optimal control that allow you to formulate abstract optimization optimal control problems and then parse them to specific solver. Very similar approach when you are dealing with ODE solvers, whether it is in Julia or MATLAB or in Python. But machine learning tools like PyTorch and TensorFlow really revolutionized all sorts of scientific domains because of the ease of use and scalability of data-driven methods that they provided with CUDA compilers and GPU computing. And what we see more and more is that domain algorithms like constraint optimization and differential equation solvers are being integrated in machine learning pipelines as so-called layers. They call implicit layers or differentiable optimization. And general term for it is either physics-informed or scientific machine learning, which is really overlap or integration of these deep neural networks with traditional procedural models, traditional equation-based solvers. And what enabled this is really software advancements in automatic differentiation. Automatic differentiation is not a new thing. It has been here for decades in Fortran, but it was not so user-friendly. It was expert-dependent. Now, anyone who can install PyTorch or TensorFlow can have automatic differentiation at scale, not only for deep neural networks, but for complex computational graphs that can involve optimization problems with constraints and dynamical systems described by differential equations. So here is very incomplete and biased literature review that samples few of these methods, like learning to solve through physics-informed neural networks that are very popular for obtaining solutions for PDEs, learning to optimize, which use exactly the same principle, sampling the collocation points in parametric space and using Lagrangians of optimization problems to obtain approximate solutions with neural networks to constraint optimization problems. System identification with nonlinear dynamical models like sparse system identification or Koopman models with basis functions represented by deep neural networks are just examples. And learning to control with those differentiable models that allow you to sample the environments and obtain the gradients from these dynamical system models for policy optimization. So when you look at all of these different scientific machine learning approaches, they have something in common, that they incorporate prior knowledge or our physics into the training through data generation or active sampling, so that's type of observational bias. They integrate structural priors into their architecture. That's like the physics-informed layers or architectural assumptions, like in convolutional networks or graph neural networks. And they include some soft constraints via penalties, like you would have in PINN approach. So these are like 3 ways how to embed the prior knowledge, and I would call them there that is fundamental constituting building blocks of physics-informed machines. So what are the similarities? When we look at physics-informed neural networks, you are sampling the collocation points in the PDE space. That represents the spatial temporal coordinates. Over those collocation points, you are evaluating neural network that is mapping these collocation points into the solution or estimate of the solution of the PDE. And you're adding some domain prior. That's the PINN layer. That's the partial differential equation that you want to satisfy. That's your equality constraint that you will be minimizing in your loss function via soft constraint penalty. So what can you do with that? You can either solve PDEs without requiring mesh-based methods, or if you have some data and there are some unknown parameters of the PDEs, you can do inverse modeling. You can estimate unknown parameters. I would argue this idea is conceptually exactly the same than what is being used in operation research in so-called learning to optimize, where we are sampling the parameters of the constraint optimization problem. And we are using neural network, again, as the surrogate solver instead of some active set or interior point solver. And now, instead of the PDE equations, the domain prior are our objectives and constraints of the optimization problem. And these can be enforced in different ways. They are so-called implicit layers that can be like differentiating through proximal operators like projected gradient method, or with differentiating through convex optimization solvers with CVX pi layers. That's one of the examples. But you are still using the same principle. You have Lagrangian reformulation of your objective function, then you are minimizing the expectations of these Lagrangian over sampled scenarios. So what can you do with that? You can solve parametric constraint optimization problems with this neural network surrogate solver that is, again, faster than traditional solver. You are paying the price offline, but once you pre-train it offline, you have neural network that is very, very fast to implement at the inference time that is very appealing for real-time optimization scenarios. One of the challenges, though, with all of these machine learning approaches that they don't provide any guarantees on constraint satisfaction. These are all soft constraint penalties what you're training on. So a lot of effort in operation research is focused on so-called feasibility restoration layers. So how do you correct the solution of this machine learning model to satisfy certain constraints? So I mentioned that CVX pi layer or some differentiable proximal operators that are being used in this community. Similar perspective on nonlinear system identification. Now, instead of sampling the parametric space of the optimization problem or PDE, we are having time series data of our observables, typically sampled in some batches of different initial conditions and length of different prediction horizon rollouts. And there are different architectures that have some prior knowledge, like in neural ODE. The right-hand side of neural network is of ODE is just a neural network, and you are using ODE solver to integrate forward in time. In deep Koopman models, you have linear transition model in the latent space, and your basis functions are deep neural networks. You are using standard loss functions in system ID, like you're matching the trajectories. You can do finite differences to approximate the first order gradients if you have non-noisy data. And all sorts of additional regularizers that act, again, as some kind of soft constraints. So you can do system ID, parameter estimation that can be very, very useful for control. That can you use in the same way, like you are solving PINNs and learning to optimize, you can sample parametric space of the optimal control problems. And this can represent different initial conditions or goal parameterizations, like changing trajectories for references or constraints parameterizations. Here, the machine learning solver is the neural network control policy. And the domain knowledge is the system dynamics model that either can come from the system identification step before or from engineering. Let's say you have your ODE model beforehand. So you can close the loop and roll out this closed loop dynamical system as a layer in this neural architecture. Then you can have these Lagrangian objective functions again, calculate expectations of those, compute sensitivities, and backpropagate those sensitivities through this unrolled closed-loop dynamical system. And this allows you to solve all sorts of complex optimal control problem like trajectory tracking and obstacle avoidance or stabilizing unstable systems. So that's what we see in our team as similarities between these different communities and methods that are emerging. But the question is, how are we going to implement those with existing tools? So for that purpose, we have been developing what we call Neuromancer scientific relation library that is a symbolic abstraction layer on top of PyTorch. So I guess most of you use PyTorch or are very familiar with library because it's the most popular deep learning framework. It's super easy to use. Dynamic computational graphs has very good support for CUDA compilers, so you can make it very efficient and scalable with GPU computing. So that was our choice. For the back end, another philosophy that we employed is modularity. Everything what you implement in PyTorch, we want to be able to be integrated in the framework. So the abstractions that we borrowed are inspired by constraint optimization frameworks like JUMP or CVXPy or PyOmo, where you formulate your optimization optimal control problem in a symbolic way. So you define variables that represent some physical properties like velocities, accelerations, or pressures, temperatures, and you formulate objectives and constraints in that symbolic way. Then you parse those objectives and constraints in the optimization problem constructor in that particular framework that is parsing that high-level abstract formulation in a solver-specific form. And then you call the appropriate solver, whether it is Cplex, gurobi, or IPOpt for that particular problem. So here, instead of parsing formulation into the solver form, we are parsing these formulations into PyTorch computational graphs. So you are creating this custom, you can call it neural architectures, although they are just computational graphs that represent either system identification problems, control problems, or optimization problems, or PINNs. So they can be represented in 4 fundamental building blocks. They have some data set. In system ID, this time series data, or in PINNs, there are some collocation points. They have some trainable function approximators like deep neural network or polynomials. They have objective functions and constraints that are at least once differentiable and continuous, and they have some loss function aggregator. The most trivial approach is to use penalty method, or more advanced approaches can use binary penalty methods or augmented Lagrangian methods, where you also have some information about your dual variables that can improve with constraint handling capabilities. So that's what our library provides as an API, and we aim to be like towards this integration of different communities. So when you do system identification and you want to use that system ID model for control, you don't need to use 2 tools, because the integration of tools in engineering practice is very painful. So that's the motivation behind our software development. If I have some time, hopefully I can show some real-time code example. I have like 8 minutes, right? Okay, so one example. I'm landing at the GitHub page, which I also showed through the QR code. Everything you need to know about the library is in the README. We come with a pip install, but for the purpose of like first contact, you don't need to install anything. You can just go and open some of these Google Colabs, and we have these different categories of problem types, like learning to optimize, system ID with neural operators, PINNs for ODs and PDEs, learning to control methods, so all of these categories that I went through. But because this is dynamical systems community, I will probably quickly go over one example on PINNs, and then one example on system ID. So everyone knows PINNs. We went through that slide again. You have neural network and you want to satisfy some equality constraints. I will skip to the problem definition, which is this simple diffusion equation with some known initial and boundary conditions. So what do we want to do? We want to sample. I'm going to skip like the code, but just show you the visualization of these 2D spatial temporal coordinates. The blue points are the collocation points over which we are going to enforce the PD equation. And the red dots here are the initial and boundary conditions which will provide the supervisory signal. Okay, so how can we implement that? Well, I will sample those data points as a tensors, two-dimensional tensors, like number of samples and a number of dimensions. And in our library, we are dealing with dictionary as a primary data type because we have that symbolic layer. We want to know which tensor is associated with which variable name, so like spatial temporal coordinates. Then we need to have some function approximator, this neural network that will learn the solution of the PDE. In this case, it's just multi-layer perceptron, but it could be any PyTorch architecture like residual or recurrent neural network. And what we provide in the library is this node class that is wrapping this PyTorch model and provides symbolic interface. So instead of mapping tensors to tensors, now we will be able to map dictionaries to dictionaries with this string for variable names. So I know that I need to have spatial temporal coordinates and inputs, and I will return the output for the neural network as a PD solution. And then we implement this variable construct that is still technically NN module in PyTorch, which means is that canonical model for neural network. So it has forward pass and differentiable backward pass, but it basically represents a pointer to inputs and outputs of the model or pointer to the data points in the data set. So here I'm creating variable for the output of the neural network and two variables for spatial temporal coordinates that will allow me to use these inline expressions to create PINN layer. So I will create first gradients and second derivatives with respect to spatial coordinates of my output of the neural network, and then use those terms to create a physics-informed layer. So the purpose of this variable is to provide user-friendly symbolic API to create this type of expressions that you can use to enforce all sorts of constraints. So how do we do it in PINNs? You want to minimize this PINN expression to be towards 0 because that's basically soft constraint, equality constraint. And for that, you also have operator overload API that recognizes the double equal sign, spawns the objective term and associated constraints that you can then aggregate in the loss function term. So you don't need to do a lot of low-level coding that can be error-prone. You have this high-level API interface that allows you to define different physics-informed loss function terms that can be aggregated with penalty methods or augmented Lagrangian methods to train those neural network models. So the same API is used for control problems, for constraint optimization problems, or for system identification. So after training this PINN, you should see this solution landscape of the PDE. So that's a very quick PINN example. And I have only like 3 minutes, maybe less. So I want to show you, let's say, neural ODE, because that would be the simplest one, but you can also go offline and see how can you solve the universal differential equations, which is basically gray box version of the neural ODE, or Koopman operators with neural networks as basis functions, or like Cindy approach trained with stochastic gradient descent. So here we assume that we have some ground truth data, that you are creating the data set by chopping it into different sequences. And we take some neural network that will approximate the right-hand side of this dynamical system model. Well, this is continuous time model, so we need to provide some solver. You could either use backpropagation through time or adjoint solver. In this case, this will be adjoint solver that actually is implementation of the original NOD paper. And then we wrap this discretized model in the node, so make it symbolic, so we can impose constraints on it. We also have this system class that basically acts as a recurrent neural network constructor on these symbolic models. It allows you to specify how many steps do you want to have for a rollout. It's very handy, especially when you want to combine system dynamics model with control policies for closed loop control. I don't have time to show that example, but that's why we have in there. So this particular example, we will have very simple tracking loss and finite difference penalty that will be implemented through these variable expressions. So you don't need to write any functions for that. Everything will be parsed by these classes for you, and basically allows you to formulate this system identification problem to learn the parameters of this neural ODE using exactly the same abstractions that we used for PINNs and for the other examples. And after training with stochastic gradient descent, you should obtain some approximation of this dynamic, super simple dynamical system and evaluate the rollout forward in time. So these are just two examples. We have way more, which I didn't have time to cover. So if you are interested, please let us know through discussions or issues on our GitHub. We'll be more than happy to incorporate them. And I want to thank to my wonderful colleagues at PNL who are co-developing the library with me and maintaining throughout last 4 years. So specifically Aaron Tuer, Madeline Shapiro, Rahul Bibnivar, Bruno Jacob, and Drgona who have been very instrumental in this project. And last slide, a little bit of self-promotion. I will be starting a new group at Johns Hopkins University starting in January, and we'll be hiring new PhD students and postdocs. So if any one of you out there are on the job market, please shoot me an email or message on social media. Thank you very much.